Hello everyone, once again my name is Rosita Orquesta and welcome to Pantasmalaya. So in the previous video we talked about the times in the process management, and then we also talk about the scheduling algorithms. We have the first come first serve, the round robin, then we have the uh, shortest job first, and then the preemptive shortest job first, which is the shortest remaining time first, and then we also have the priority based scheduling. And then today we will be having the highest response ratio next scheduling algorithm. So the concept of um, highest response ratio next algorithm, a scheduling algorithm, is that we will be looking into the waiting time and then the service time or the burst time of each of the processes. We will have to compute these two, the waiting time and then the burst time, so that we can get which of the processes in the queue it has the highest response ratio to be given a time in the CPU next after the current process. So I have here prepared a sample data for the highest response ratio next scheduling algorithm, and this is the formula. So RR, or response ratio, yep, the response ratio next is equal to the waiting time plus the burst time, and the answer would be divided also by the burst time itself of the current process. So to experience the to actually experience the the concept of highest response ratio next scheduling algorithm, uh, highest response ratio next scheduling algorithm. We are going to, or by using this data here, the table, we are going to create a Gantt chart. So say we have the time, the arrival, and then the execution for each of the process. So looking at the arrival time, it starts with 0, so we'll have 0 here, and then it has up to 8. So let's say we can at least have it at 10, right? File series, so 9, 10. Okay, and then we'll put this into a borders or table. Okay, and then looking at the burst time, we have 3 plus 7 plus 5, that's 15, and then 21. So we need at least 21. So we'll copy this one. So this is 11. Okay, so we have now at least until 21. uh, we will treat this time as seconds. So let's assume that the time slice is in seconds. Okay, so with this data, let's first uh, look at the arrival time of each of the processes. So it says here that P1 arrives at 0. So we'll mark here P1, P2 at around time 2, uh, time 4 for P3, and then time 6 for P4, P5 is around time 8. Now to make it more visualized, we'll try to put a color in each of the processes. Red, yep, yellow. This one will be green. P4 will be blue. P5 should be that one. Okay. So okay. So since on the time zero, process one has arrived and it is the first and only process in the queue. So no other process arrives at zero but just the P1. So we are going to execute or give the time or time of the central processing unit to P1 for at least for how many time slice. So say P1 has a burst time of 3, so we'll give it 3 counts of time slice. Now at around time 2, P2 has arrived. But then, just like the concept of any other scheduling algorithms, unlike the preemptive shortest job first, if there is a new arrival, it will be put in queue. It will not stop the process of the current job and compare the burst time or whatever. It will just let the current job to finish its execution in the central processing unit. So it will just put the new process, the new arrival process in the queue. Then at around time 3, since there is no other process, just the process 2, so the central processing unit will give a time to process 2. For how many burst times? It has 7. So we'll count 7. We'll color this yellow. So 1, 2, 3, 4, 5, 6, 7. So since at around time 2, as you can see, at around time 2, P2 has arrived, and then there is no other process that arrives at P3. So we have to give the time of the central processing unit to P2. And then since P2 has burst time of 7, so we'll have to count 7 times slice. 1, 2, 3, 4, 5, 6, 7 times slice. And then within this 7 times slice, process 3 has arrived at time 4, process 4 has arrived at time 6, and process 5 has arrived at time 8. Now, since there are 3 processes in the queue, at around time 10, we will decide which of these processes will go first and which of this process will go last or next. So what we are going to do is compute the response ratio for each of the processes. So we have here the P3, the P4, and the P5. Okay, so the formula is response ratio next equals to waiting time plus the burst time, its burst time, and then divide it by its own burst time also. So since this is Excel, we are going to put the equal sign first, and then as you can see in the unfinished Gantt chart, we are now at around time 10, slice time 10, or 6, 10, 10th seconds. So we're going to put here 10. But for process 3, it is not that process 3 has arrived at around 0. It arrives at around time 4. So we are going to count or to subtract a certain amount of time slice from time 10. We are going to count from 0. So 0, 1, 2, 3. That is 1, 2, 3, 4. So we're going to subtract 4 from the 10. So because it's not really 10 seconds that P3 waits before execution if it is P3 to be executed and next to P2. But since it arrives at around 4, so we have to subtract 4 from 0 to 3. And then after subtracting, we're going to add its burst time now. So the plus burst time here. So P3 has a burst time of 5. So we're going to add 5. And then after that, it says we are going to divide the result by its burst time. So divide 5. So enter. So it has a 2.2. So the response ratio of this P3 is 2.2. And in the same manner, we're going to do that also in P4. So still P10, ano, time 10, and then subtract it by 1, 2, 3, 4, 5, 6. So 6 times slice to be subtracted from the 10. Then add its own burst time, which is 2, and then divide it, the result, by 2, and then we get 3 for the response ratio of P4. And then for the P5, still we are going to compute 10, and then subtract how many times slice. 1, 2, 3, 4, 5, 6, 7, 8. So 8 times slice to be subtracted from 10, then add its own burst time, which is 4, and then divide the result by its own burst time, which is 4. So we have 1.5, 3, and 2.2. Now, as you can see in this result, the highest response ratio is on P4. So at around time 10, we're going to give a chance time for processing to P4 or process 4. So it has 2 burst time. So we accommodate 2 times slice for the uh, P4, P3, I mean P3, no, P4. I'm sorry. So this is P4, so should be in blue. Uh, yeah, okay, so P4. And then at around time 12, we are to compute again. So this P4 is already done. We'll remove that one, and then we are going to compute the response ratio for P3 and P5. So instead of 10, it is now at around 12. So we're going to change this to 12, and then here to 12. Okay, so as you see here, P3 has 2.6, while P5 has 2. So therefore, the highest response ratio is given to P3. So we're going to uh, execute job 3 on the central processing unit next to P4. So P3 has a burst time of 5. So we'll color this green and we'll count up to 5. 1, 2, 3, 4, 5. Okay. And then for the last one, now that it's only the P5, we are going to give the last time slice to P5. So this is color 1, 2, 3, 4, 5. Nope, P5 has 4 burst time. Um, P3 has 5. 1, 2, 3, 4, 5. 1, 2, 3, 4. Okay. So let's check it again. So P1 has 3 burst time. 1, 2, 3. P2 has 7. So 1, 2, 3, 4, 5, 6, 7. And then P4 has 2. P4 has 2. 1, 2. P3 P3 has 5. 1, 2, 3, 4, 5. And then P5 has 4. 1, 2, 3, 4. So 20. So this is the complete time slice or Gantt chart for each of the processes using the highest response ratio next scheduling algorithm. Now let's talk about threads. So what is threads? A thread is a basic unit of CPU utilization. So consisting of a program counter, a stack, and a set of registers. It also has a thread ID. Traditional traditional processes have a single thread of control. So there is one program counter and one sequence of instructions that can be carried out at any given time. While the multi-threaded applications have multiple threads within a single process, so it's have each of it having their own program counter, the stack, and set of registers, but sharing common code, data, and certain structures such as open files. Are threads useful? So the answer is yes. The threads are useful. The threads are very useful in modern programming. So whenever a process has multiple tasks to perform independently of the others. So this is particularly true when one of the tasks may block and is desired to allow the other task to proceed without blocking. And then, for example, in a word processor, if we talk about multi-threading, uh, in a word processor, so for example, a Microsoft Word or any other word processor that works like the Microsoft Word, a background thread may be checking the spelling while you are typing your word, and then it also will check the grammar, and then while the foreground thread is the processes by accepting user input or keystrokes. When you type letters on your keyboard, it will be displayed on the worksheet of your word processor. So those are an example of a multi-thread. So and then it could have another thread, a third process, a third threads that it will load the images from the hard drive, and it could also have a fourth sub process or threads which is to periodically automatic save backup of your file that is being edited. So, another example is a web server. Multiple threads allow for multiple requests to be satisfied simultaneously without having to service requests sequentially or to fork of separate processes for every incoming requests. So there are also a lot of benefits when it comes to having multi-threading. So there are four categories of benefits of multi-threading. The first one is responsiveness. So one thread may provide rapid response while the other um, threads are blocked or slowed down doing intensive calculations. The second one is resource sharing. By default, threads share common code, data, and other resources, which allows multiple tasks to be performed simultaneously in a single address space. And it also uh, beneficial when we talk about economy. So creating and managing threads is much faster than performing the same task for processes. Scalability. So utilization of multiprocessors architectures, a single threaded process can only run on one CPU, no matter how many may be available, whereas the execution of a multi-threaded application may be split amongst available processors. And let's talk about a multi-core programming. So a recent trend in computer architecture is to produce chips with multiple cores or CPUs on a single chip. So if we try to look back at the previous years, I don't know if you have heard the Pentium series of Intel, and then comes the cores, the dual core, the quad core, core 2 do, which has two cores, and then it has four cores, and then later we have the Core i series, the Core i3, the Core i5, and the Core i7. On uh, the other computing machine like a smartphone, it has the octa cores series, and then for the other the competitor of Intel, we have the Ryzen 3, Ryzen 5. So those are multi-cores, has multiple processors or multiple cores or CPU on a single chip. Then a multi-thread application running on a traditional single core chip would have to interleave the threads. Okay, so that is multi-core programming. So when you say interleave, is it is like giving space to another threads. Like if you try to imagine a a, a, a time slice, so we have like five time slice, and then the first slice is given to this thread, and the second slice is given to this other threads, and so on and so forth. So you may say it is like a scheduling algorithm. So, but having this multi-cores or this multi-threading um, technology in computing, it also possesses programming challenges, and these are the challenges that we're to face when due to the implementation of multi-threading. So, for application programmers, there are five areas where multi-core chips presents new challenges. First one is identifying the tasks, examining applications to find activities that can be performed concurrently. And the second one is balance, finding tasks to run concurrently that provide equal value. Like you don't have to waste a thread on a trivial task. And then the third one is data splitting, to prevent the threads from interfering with one another. And the fourth one is data frequency. If one task is dependent upon the results of another, then the task needed to be synchronized to assure access in the proper order. And then the fifth one or the last one is testing and debugging. Inherently more difficult in parallel processing situations as the race conditions become much more complex and difficult to identify. So, so again, a multi-thread is like you have this application, you have this system, you have this program, and this main program has and this main is made of multiple threads. Is like you have one process, and then this process has multiple sub processes, and each of these processes consumes resources independently, works simultaneously to produce one output for that whole application. So that is multi-threading. If you have any questions and clarifications, comment down below. And thank you so much.